I want to talk tonight about nucleophilic substitution reactions and the factors that affect them. And I want to start off by talking about the role that the leaving group can play in this reaction. And I want to start this discussion by considering two similar but different reactions. The first reaction I want to look at is this one, where I have a bromine as my nucleophile and my OH is my leaving group. And what I want to say about this reaction is that this reaction will not happen. No matter how long you wait, you're not going to get any appreciable amount of this bromo-containing product. The next reaction I want to consider is this one. And in the second reaction, we start with the same alcohol, but first we protonate it. Then we try to get it to react with a nucleophile, the same nucleophile in this case. And what I'm going to tell you about this reaction is that this reaction will happen readily. Well, what's the difference between these two reactions? If we look, what we notice is the difference is the leaving group. In reaction 1, this OH is the leaving group. On the other hand, in reaction 2, it's H2O that's the leaving group. And I should emphasize that this is OH minus as a leaving group, and H2O has no charge on it. So when OH minus is a leaving group, the reaction is slow. When H2O is a leaving group, the reaction happens easily, readily. Why is this? OH minus is a bad leaving group, and H2O is a good leaving group. And what is the sort of physical characteristic we're going to look at in order to allow us to recognize that something like OH minus is a bad leaving group and H2O is a good leaving group? The thing that we want to look at is base strength. In general, OH minus is a strong base and H2O is a weak base. And that's sort of the general correlation we're going to use, not only in this case, but always, the relative base strength of our leaving group. Because the correlation that we can make is the stronger something is as a base, the worse it is as a leaving group. So OH minus is a pretty strong base, bad leaving group. H2O is a weak base, and it's a good leaving group. Now, a lot of the leaving groups that we're going to look at in this class are halides, iodide, bromine, chloride. And we can use this rule that we just talked about, stronger base equals worse leaving group, to look at the halides in terms of leaving group ability. So if I've got a list of the 4 common halides here, fluorine, chlorine, bromine, and iodine, or iodide I should say, and usually we think about the strength of a base in terms of its conjugate acid. And so I've got HF, HCl, HBr, and HI. Of this list, HF is the weakest acid. That means fluoride is the strongest base on this list, and it is a poor leaving group. We don't usually use fluoride ion as a leaving group. On the other hand, HI is the strongest acid on this list, meaning I minus is the weakest base, and I minus is the best leaving group on this list. And chlorine and bromine fall in the middle here. So we can use this rule in this association, and we'll use this rule in this association a lot. The stronger something is as a base, the worse it is as a leaving group. And alternatively, we could say it in the other way, the weaker something is as a base, the better it is as a leaving group. So most of our leaving groups, good leaving groups, are weak bases.